Thank you very much for the invitation. It's my pleasure to be here. I'm going to give a survey on random matrices, and actually I will focus on only one aspect of this area. Here's what we call random matrices. Basically, you can imagine it is a matrix when every entry is a random variable, so it generates a probability space. So in the entry, we usually write in a random variable, which means 0 and variance 1, just for normalization purposes. You can think of, example as real Gaussian or complex Gaussian. And for this talk, which is for combinatorial audiences, we will actually consider the Bernoulli random variable. So it is just a coin-flip random variable. It takes value 1 and minus 1 with probability half. Right? So you have a matrix. For every entry, you flip a coin and write in 1 or minus 1. So there are two models. The non-symmetric models, so every entries are independent. And the symmetric model, then of course you have only independence up to the symmetry. So only the upper triangular entries are IID. Right? So you have only this part are random, and the other part, the lower triangular entries are just the mirror reflection of the upper part. Yeah, so I use letter SYM here to denote the symmetric case. And usually for many models, for the symmetric model, as I said, upper triangular, I do not emphasize the diagonal. And for the diagonal, we are allowed to have different random variable rather than Bernoulli. And it usually do not influence the analysis too much. There are related models that come from theory of random graph. Basically, you can take a random graph and take the adjacency matrix. For instance, if you take a random graph Gn half, namely you have n points and connect every 2 points with probability half, and then in the adjacency matrix for this position it is either 0 or 1 according to the edge is there or not. So this will give a model of random matrices when you write not plus minus 1 but 0 1, right? And this is a symmetric model. Okay, so random matrices connect many areas. It is very big topic though. It was started in the 1920s by statisticians actually, and then in the 1940s it was considered by numerical analysts. Von Neumann started to consider problem of complexity of computational problems. At that time he was involved with computing devices, as we know. So there's the series of 5 papers of von Neumann and Goldstein which established the numerical analysis as we know today. And one of them deal with the problem of computing with big matrices. Mathematical physics and probability, Wigner, Eugene Wigner was the guy who started this, and he introduced random matrices, symmetric random matrices, to study heavy nuclear. So what he observed is that the behavior between the gap of eigenvalues of a random matrix is very similar to the gap between energy levels of nuclear, and he used random matrices as the model to analyze these nuclear processes. Yeah, so there is, and in combinatorial it was introduced. I think Comblos was the first guy to consider this, and there is various combinatorial problems that I will discuss today. So the first two topics are for different talks. So for this talk, I will focus only on the third topic. And there's a lot of interaction between this area. Yeah, so here's a few combinatorial problems that people usually look at. The first one is a singularity problem. So again, we have a matrix, right? N by N matrix. Now you write to each position, well, plus minus one number. And the question is that how often is this matrix singular? Yeah. So after, say, you answer the first question, and well, you may guess that the answer will be that it is singular, very, very rare. Namely, that most of the time it will be a full rank matrix, meaning that the determinant will not be zero. And so the next question is that, okay, if the determinant is typically not zero, then what it is, right? So what is a typical value of the determinant? A parallel question is that, okay, if you replace the permanent by the determinant, then you can ask the same question just because of similarity. And you can ask, for instance, okay, not only things about the eigenvalues, you can ask things about the eigenvectors. So you take say a symmetric random matrix, then you have eigenvectors which form an orthonormal basis. So how does a typical eigenvector look like? Does it look like a random vector, or does it have something special? So these are a few things that I want to discuss today. There are more questions, but yeah, as I said, it's a huge topic.
I don't see a difference between determinant and permanent.
Well, the difference is in the definition, right? So the definition of determinant of the minus this, and the permanent doesn't have this. So the permanent can be quite different from the determinant for the same matrix. For instance, if you take a matrix with positive entry, the permanent is always positive by definition, but the determinant can be negative. Okay? Yeah, but formally they look quite similar, just the signs are different. Okay, so the first one is actually my favorite problem, is a singularity problem. Okay, so we ask for the probability that the matrix is singular, and there are two cases, two models, as I said, the non-symmetric model and the symmetric model, and the analysis of the two are quite different. Usually, well, in this area, in the combinatorial area, combinatorial theory of random matrices, then the symmetric case is actually harder because you lose independence, right? So in the non-symmetric case, every entries are independent from the other. But here, well, you know, this guy are dependent on the upper triangular entry. So the lack of independence will cause you some problem. Okay, so question is, what is Pn? Okay, there is a very famous conjecture, and notoriously hard, namely it assert that Pn is roughly half to the n. And you can see why the half come very easily, because if the matrix have two equal rows, say the first row and the second row of the matrix are the same, then of course the matrix is singular. And the probability that these are the first two rows are the same is easy to compute. Well, you can have the first row arbitrarily, and the chance that the second row match the first row completely, it will be half to the n, right? Every entry have to match the upper guy. And yeah, then you can have the extra n square here, because you can choose any two rows you want, and you can choose any two columns and so on. So you have this lower bound, which is the lower bound for Pn, and the conjecture is that the lower bound is actually more or less the upper bound. Okay. Any question so far?
This is trivial.
Yeah, the lower bound is trivial.
Yeah. Somehow two factors meeting. Experience comes out twice n to 2 because we can choose.
Right.
But two rows can be different by only signature.
Yeah, but I say two equal rows here, right? So,
Yes.
so yeah, you can have better lower bound.
Twice of this one.
Sure. But it is technically correct.
Yeah, it's not. It's misleading, but it's not incorrect.
Okay. Yeah. And to illustrate that it is hard conjecture, yeah, we are aiming for very specific. Well, it's first of all it is exponentially small in n, and with base we are aiming for a specific base here, right? It should be half. But even to prove that Pn goes to 0 with n is not so easy. It was first proved by Combinatorial in '67, and his proof is quite long. It's like 10 page long. I have a very short proof which is just half a page, but I will show it at the end of the talk if they have time left. Yeah, I will show this proof, just give you some flavor about the techniques. Yeah, but even this is not entirely trivial. Okay, so here's actually the proof, but yeah, that's these 2 pages. But yeah, let me show it at the last 15 minutes of the talk. I don't want to get too involved at this point. All right, so Combinatorial proved something going to 0, and next he proved that okay, it can go to 0 polynomially fast, 1 over square root n. And in '95, Kahn, Combinatorial, and Symmetrical were the first people who made the breakthrough showing that actually it does go to 0 exponentially. So it is, yeah, well, important thing here is that the constant is less than 1. And actually, even if you optimize the parameters in his paper, it comes out at 0.999. It's very close to 1, but less than 1. Yeah. It is not hand waving. It's very hard to improve. It is to 0.9. Believe me, it's not. Yeah. So, but 3 years ago, Terence Tao and I can improve the base to 3/4. And it needs a significant new idea and very interesting connection to a field we call additive combinatorics. Yeah. So idea from probability and linear algebra alone cannot solve the problem somehow, or cannot lead to the improvement. So we need some other kind of tools. And the latest record is by Jean Bougan and I and my student Philip Wood. We improve the base from 3/4 to 1 over square root of 2. So it is halfway to the conjecture. So the conjecture is half to the n. The current bound is half to the n over 2. Yeah, so here's the few tools I want to mention. The first one is something we call the dominating principle by Hollas, developed back in the 1970s. Yeah, so it gives a tool to estimate sum of Fourier coefficients of certain function, and that idea was used as well in the KAIST paper. So the new ingredient Terence Tao and I introduced from additive combinatorics is what we call the inverse Littlewood-Oxford theory, and that now allows you to derive this kind of bound, the 3/4 bound, or the 1 over square root 2 bound, very easily from just simple trigonometrical inequality like this. So what we want to do is, yeah, so by the end of the day, after lots of argument, the 3/4 come from this simple inequality that you can dominate the absolute value of cosine by 3/4 plus 1/4 of cosine of 2x, right? Which is anyone can prove by by just elementary, by high school algebra. The extra idea from the paper with Bougain and Wood is something we call the fractional dimension argument, and this gives you a better way to dominate. So namely, we can dominate not cosine but cosine square by half plus half of cosine 2x. Actually, it's equality, and well, because we square this, right, and then actually we have to take the square root of half here. That's basically. Yeah, so if you can find a better thing, namely you raise it to power 4, you find some other constant, then it will be that constant to the power 1/4. But I believe this is the best thing you can do. So it's yeah, so yeah, this is a little bit about the inverse Littlewood-Oxford theorem. That maybe I also skip because I want to focus on just matrices, and if we have time we come back to that later. Okay, so again still the singularity problem, but now the symmetric case. As I told you, symmetric case is usually much harder than the non-symmetric case. And so, yeah, so now again we're considering Pn, but with the extra symbol sim here, and we ask the same question. It was conjectured by Benji Weiss in the 80s that actually this goes to 0, which is not surprising at all, right? In the non-symmetric case, the conjecture is that it goes to 0 exponentially fast. But, well, now of course Weiss are clearly aware of Komlow's paper, but yeah, but still he make a much less ambitious conjecture. And I think probably Komlow's should conjecture is as well. It's hard to imagine he didn't consider this question. It's so obvious. Yeah, but it took quite some time. In 2005, my student Costello, Tao and I can prove it really go to 0, and it go to 0 polynomially fast, 1 over n to the and recently Costello improved about to 1 over square root n. And the reason for 1 over square root n is very interesting. 1 over square root n is named, well, it seems to be the n of the limit of our method, and it comes from a lemma which is sharp. So let me tell you what this lemma is about. This is in itself an interesting topic. Not okay. Yeah, so let me tell you the lemma. Let me tell you the first of all, the Littlewood-Oxford problem. So if you went to the talk, my talk up at the KMS AMS meeting, I already mentioned this, but I can do it again. So the problem is, the problem of Littlewood and Oxford from the 1940s is the following. You have, well, one version is the following. You have non-zero integer, and you consider the linear form A1C1 plus up to ANCN when Ci are just this coefficient. And the theorem they prove also by Erdős, actually Erdős proved it in the stronger form, is that the probability that L equals 0 is bounded from above by a constant over square root n. And to see that where the square root n comes from, you can take the case that A1, A2 up to AN equal to 1, right? And let n be an even number. So in this case, that L is just the sum of random coefficients, and the probability that L equal to 0 is just the probability you have exactly n over 2 minuses and exactly n over 2 pluses, which is n, choose n over 2 to the n, and by Stirling formula you know that it is some constant divided by square root n. So we show not only that this is the upper bound, but it is a sharp upper bound. Now for the quadratic, for the symmetric case, and this was used in the Comblo's paper, Comblo's proof of the non-symmetric case. For the symmetric case, actually we need the quadratic version of this, namely instead of the linear form L, you need to consider a quadratic form. Say Q is now you have a set of Aij, non-zero integer, and you consider the quadratic form Aij times Ci times Cj. And you ask the same question, so what is the probability that Q is equal 0? And well, in the paper of the Joy paper with Costello and Tao, we can prove it to be n to the minus a quarter, which gives us about for the Benchy-Weiss problem. But then Kevin optimized it, and he can actually more or less prove the sharp bound like n to the minus half plus epsilon. And you see that it is sharp up to the epsilon term because simply you can take Q to be L squared, right? It's just the square of the linear form. And for linear form, we know that 1 over square root n is sharp, so it's sharp.
CI is plus minus 1 or?
Oh, CI are plus minus 1, but it generalized to more general settings. So you can take other random variable as well. Yeah. Plus minus 1 are easiest to imagine, right? To sort of, yeah. Well, well, actually, all of the theorems I say here apply for much more general distribution rather than plus minus 1, but it's easier to present the talk this way. Okay, so one question here which doesn't have anything to do with the random matrices but may be interesting in itself is that what can you say about higher degree polynomial? So for cubic polynomial, again I conjecture that the bound should be 1 over square root n, but nobody knows how to prove that yet. Right, so here's the conjecture I want to make is actually even for the symmetric case, the non-singular, the singular probability is 1/2 to the n, and we see that the lower bound is clearly the same as the previous lower bound. Right? And we are very far, unfortunately now it's quite far, well, still very far from here. Yeah, the approach that we have with Kevin here is well, it seems to probably, somebody put a lot of work on it, it can improve. Maybe it can be used to improve the exponent, but it's not clear how to do an exponential bound yet. Okay, so quickly, this thing I will go over quickly is that, okay, yeah, another model for random matrices is that you can take the adjacency matrix of a random graph, right? And now, yeah, so instead of plus minus 1, we have 1 and 0. And actually, the density of the graph is P, then the 1 and 0 is biased, right? So P can be very close to 0. So you have 1 with very small probability, not necessarily 1/2, right? It can even depend on n. So if P is a constant, not 1/2, but say 1/4 or 1/10, you can prove the same result that the matrix is almost surely non-singular. What about P going to 0 with n, right? So typically in the theory of random graph, we care a lot about the case when P is quite small, close to be 1/n. Now there's the threshold. You can see that the graph will KAIST to become non-singular because of a very simple reason that it will have isolated vertices. Right? So when the graph have isolated vertices, what you see is that in the row, so this vertex is not connected to anything, and actually the row corresponding to this in the adjacency matrix is the O0 row. Then of course the rank cannot be n. Right? That is a very simple reason. So if P is less, and the threshold for having non-isolated vertices we know is log n over n. So yeah, of course if P is less than 1 over epsilon times log n over n, then the graph is non-singular. And actually,
could you remind me what is P for the random?
What?
What is P for the?
Oh, P. Yeah. P is the density. So namely, you generate the graph this way. You have n points, and for every pair I and j, you connect them with probability P, and do not connect them with probability 1 minus P. Okay. So P is a probability. You see a 1 in the matrix.
The 1 then is connected.
Yeah. And so with Kevin, I can prove the matching bound, namely that actually having non-isolated vertices or having isolated vertices is basically the reason for the graph to be singular. So it is the threshold for.
So you fix epsilon there?
What?
Fix epsilon.
Yeah, for any small epsilon.
Yeah.
So if you care a lot, you can write instead of epsilon something like 1 over log n, something very tending to 0 slowly. And actually, even below this threshold, now say if P is C times log n over n, when C is less than 1 now, namely that the graph is guaranteed to be guaranteed to be singular, then actually you can compute the corank of this graph. And it coming from small obstruction. So clearly the corank, if you have corank, if you have isolated vertices, then of course this contribute to the corank because every single isolated vertices give you a 0 row. So the corank increase. But there are other reasons. For instance, if you have a point like this in the graph, you have exactly 2 neighbors with no other connection, then actually these 2 guys, U and W, the row corresponding to U and W will look exactly the same in the matrix because they have the same neighborhood. Right? So 0 means no neighbor and 1 means neighbors, and they have the same neighborhood, and of course the row corresponding to them are the same. And that also contributes to the corank because it gives you 2 same rows. Yeah, and basically you can characterize all these small constraints that give you the corank, and that you have an exact bound there. And if P is something like C over N, then there are people, Boden and Large, who can compute the rank asymptotically. But I don't know if they can, they can compute characterize the corank in this way. Right? So there's still things to be done in this range of neighborhood. Yeah, so here's the conjecture that is a little bit embarrassing to me. Okay, so we know everything, lots of things about the Adjacency graph. There is the model, other model for random graph called the random regular graphs. Right? Okay, so random regular graph is something like this. I give you the degree d. Well, you can take a number 10, or you can take a number like square root n, whatever, any number between larger than 1. Say. Okay, and now you consider every graph, regular graph on d points, on n points with degree d. Right? So there will be lots of graphs. You consider all of them, and you choose one uniformly randomly. Right? So you have maybe a big box of 1,000 graphs, and you choose one of them. Right? And the conjecture I want to make here is that with high probability, these graphs are non-singular for any fixed number, for any number d between 3 and n over 2. And nobody knows anything. Yeah. So question is, why it's not 2? Why did I start from 3? The reason is not 2 because random regular graph with degree 2 is just union of circle. Union of disjoint circle. The only graph which have degree 2 regular graph. And I think if the length of the circle is divisible by 4, then actually the adjacency matrix is non-singular already. So actually if d equal to 2, then the matrix is singular. But for d larger or equal to 3, the graph is connected, and I don't see any reason why it should be singular. Okay. Okay, this is not so interesting. Okay, so now let me go to the determinant. Okay, so again, yes, we already talked about this. We know that the graph is at least with high probability non-singular, so the determinant in absolute value is non-zero, and you can ask that, okay, if it is non-zero, how big it is, right? So it was shown by Turan in the 1940 is that at least we know the expectation of the determinant square. And this is a simple calculation. I want to show. If you haven't seen it, then you may like it. But if you've seen it before, then never mind. Okay, so how? Yeah, so it's an exact formula, right? It's expectation of the determinant square equal and factorial. So the determinant looks like this. It is a sum of over O permutation, right? Minus 1. The sign of the permutation, product of Ci. Okay, so the Cij are the entry of the matrix. Okay. Well, the thing is that if you square this, then of course you have to take a sum over O pair of permutation. Right? Take the minus the sum of the two sign and take now the product of two n terms instead of n. Okay, so now if you take the expectation of this, then by linearity of expectation, you can take the expectation of this, every single term. Now, but we know that the entries are independent, right? So, if we can, well, you can further put the expectation inside like this, then it would give you 0 because the expectation of this guy is 0. Right? So whenever you can do that you have 0. The only case you cannot do that is when C and pi are exactly the same. And what you would have is just a product of this square, and you cannot do that trick. Right? And now if you put the expectation inside, it doesn't give you 0, it gives you 1. Right? And so you have exactly n factorial term, diagonal term, and it gives you n diagonal, n factorial. Alright, okay, so that is a cute computation. And if, again by Stirling formula, you can write it is something more or less of order n to the n. Right? It is actually super exponentially large. Yeah, the conjecture here, I think it's sort of a folklore that people expect that, okay, if the determinant square is like this, then the determinant should be the square root of this, right? There's actually no doubt. Well, at least it's true as an upper bound, right? by just Markov inequality. But it's not so clear as the lower bound. In fact, it was not clear that it's almost surely it's not zero. Okay, so yeah, about 5 years ago we can prove this. This is now the fact. So not almost surely, not only the determinant is non-zero, it is as large as you expect from the two-round calculation. Yeah, so here I give you one idea, which is a geometric one. So we see some additive combinatorial idea. Now I want to show just slightly a small idea. Is yeah, and the idea here is very simple. It's just a geometrical interpretation of the determinant. So the determinant, if you have now, if you look at the matrix, which have rows, say x1 up to xn, right? Then the determinant is the volume of the parallel like pipette spanned by this vector. Right? So it is an n-dimensional box. And the volume of these boxes is easily computed by the base time height formula, right? So you take this guy, you multiply by the distance, you get the area of the two-dimensional box. You multiply by this distance, you have the volume of the three-dimensional boxes and box and so on. And the idea here is actually much of this distance now are random variable, but they are very good random variable in the sense that they are strongly concentrated. They behave like a constant with high probability. So this is the lemma. It says that if you take a random vector, so remember that the distance is from a random vector to some subspace, right? And the lemma is that if you take a distance from a random vector to any subspace of dimension d, then with high probability this distance is square root of n minus d plus some small error, maybe 10 or something. Okay, so this takes care of most of the distance. At least n minus d is so small that the error will overtake this, and so that the last few distances we have to do some other thing to take care of this. Okay. Okay, so now you are getting warm up, and then you get more ambitious. Then there are more questions, which I don't know the answer. Okay, so the question is that we know, yeah, say before the singular probability is the same as the probability that the determinant is zero, right? And we know that, okay, we don't know the base, but we know that it's exponentially small, both from below and above. What about the case when I replace the value 0 here by some other number, any other integer? And my conjecture is that it will no longer be exponential. The behavior will change. It will be exponential in some function that is super linear in n. In fact, I think it is not. It will not be constant to the n. It will be some constant, or it will be n to the n. But I don't know how to prove that. Another question is that, yeah, you can ask, well, now we know what is a typical number. You can ask about the limiting distribution. And here, what I think is that it should, well, if you take the log, the determinant should have log normal distribution, basically. And there are some Ukrainian mathematicians who claim to prove it in the 80s, but it's very hard to, basically nobody understood this proof, but probably it's true. I think Costello had the idea, but I think he could more or less prove it, but yeah, but the Ukrainian will get very mad, so we're still thinking of is it worth it or not. Okay, so yeah, maybe I skip this concentration issue. Yeah, okay. What about permanent? Okay, so I told you the case about determinant, right? And for non-symmetric, yeah, so everything now is non-symmetric. Yeah, so, yeah, recall that the determinant is this, right? The permanent, as I said at the beginning of the talk, is more or less the same expression, just missing the -1. And in the random setting, it's very similar because you know that this guy take value 1 and -1 anyway. So even if you miss the -1, it's hard to imagine that they behave differently. For instance, the two-round calculation is the same, right? If you square the permanent, you can repeat the whole calculation. There's the -1 to the something doesn't play any role. You will have the same n factorial. So it's natural to conjecture that we have the same behavior as the permanent. On the other hand, it was already a long-standing open conjecture that the permanent is not 0. Right? So it is a permanent version of Gounod's theorem from the 1967. It has been open for quite a while. And the reason is that for determinant or for singularity problem, it's very important to use linear algebraic or geometric interpretation. So the probability that the determinant is 0 is a probability that the box at volume 0 is a probability that all the vectors lie on the same hyperplane, right? Yeah, none of that apply for the permanent. The permanent, despite the fact that it has formally it looks close to the determinant, none of the interpretation, algebraic or geometric interpretation work for the permanent. That's why it was hard. Yeah, anyway, but we found another way. It's completely different argument to prove this theorem. But, so we have the permanent version of the determinant result, but by a very different idea. It has nothing to do with this box and height box volume argument here. And here, more strangely, I don't even have conjecture about the limiting distribution. As I said before, we suspect that it will have log normal. The determinant have log normal distribution, and I think Costello can prove it. But actually, it's not clear what happened with the determinant, with the permanent. It's not. For instance, for the determinant, it's very easy to prove things for the Gaussian case, but for the permanent, there's nothing is known. Yeah, okay, and then I can be now, sort of again very ambitious. I can ask the singularity question for the permanent, right? So almost surely means that here the permanent is this big with probability tending to 1, and I can ask, okay, what is the probability that the permanent is 0? Right? So for the determinant, we know that the conjecture is half to the n, and we can prove half to the n over 2. For Qn, I know only polynomial bound, something of this form n to the minus epsilon. Nothing exponential. So the current bound is this, as I said. And the truth may be even, the truth here is very interesting, it's even less than exponential. Because for the determinant case, you have a simple reason for the matrix to have singularity, because you have two rows which are the same, right? But for the permanent, there's no simple reason for the permanent to be 0. Okay. What else? Yeah. And the two things I said apply only for the non-symmetric case, right? Well, now for the symmetric case, again, well, now the two-round computation is not so nice anymore. If you compute the expectation of the determinant square, it will no longer be exactly n factorial. Right? So you can try it by yourself. It's good exercise to compute it exactly what it is. Because you know that the Cij and Cji are the same. So on the other hand, they will still be of the order n to the n. And so you can conjecture, well, now if we don't care about the exponential term, then you can conjecture have the same conjecture as before, as in the non-symmetric case. So out of this, so the main difficulty here you can see is that the rows are no longer independent. Namely, recall the case when we do the determinant for the non-symmetric case, so we do the high time-based formula, right? And it is very important is that you have the distance from a random vector to this subspace. And we can prove that distance is highly concentrated. But the rows for the symmetric case, they are not independent. Actually, the last few rows are very bad because, say, if you know the first n-1 row, then actually we know the last row more or less exactly. Only one random bit left. There's nothing random in the last row. Actually this is the main difficulty for the whole business when we go from non-symmetric to symmetric. You see that every problem gets harder. Every combinatorial problem gets harder. There are problems which are easier, but not in this talk. Okay, so between the two, I can prove, tau and I can prove the first one by a very different reason. Now it goes from the whole through the whole process of, it have a lot of mathematical physics in it. But no longer this simple. And I don't know how to do the permanent for the symmetric case. I don't know how to do, actually I don't know how to prove that the permanent for the symmetric case is non-zero with high probability, right? Let alone that it is this big. So there's always two steps. First of all, you show that it's non-zero. Second, you show that it is this big. The third step is to have limiting distribution. Okay, so last few words about the eigenvectors. So there's only one result here, but it's more or less probably contain everything. So one thing, for eigenvector, it's more reasonable to talk about the symmetric matrix because non-symmetric matrix actually not always have eigenvectors, right? First of all. But for symmetric it's very nice. They have exactly n eigenvectors and they form an orthonormal basis. So I normalize all this guy and they will have length 1. And the question here is that how do this vector look like, right? There is so the sub question is that what is the largest coordinate of an eigenvector? So eigenvector is a vector of length n, right? With real coefficient, real coordinates, and the norm is 1. So if you look at the maximum coordinate, it should be larger than 1 over square root n, right? Because sum of the square is 1. And the result we can prove is that actually with high probability this lower bound is an upper bound as well, up to the linear of 1/3. So what you can conclude from here is that actually this eigenvector is very balanced. It doesn't have too large coordinates. All the coordinates are small. And there are other facts that we can prove. I think this much I want to say about the theorems. I have, I don't know, 10 minutes left, so you can choose either we stop here and you go home and everybody is happy, or or I can show you one proof, the proof of the Combinatorial theorem that I promised at the beginning of the talk. So it is a proof of this of the very first theorem of the whole business.
Before you go on,
yes.
This permanent.
Yes. Okay. Please.
Does it have any mathematical meaning? Why?
It comes from exterior algebra, but not. I think it's not so much connected to linear algebra. somehow what people doing exterior algebra like that. Yeah, but well, for people doing graphs, it has some meaning. For instance, the permanent of the adjacency matrix count the number of perfect matching in the graph. Yeah, but and for people in so I skip a topic on computation of the permanent. So there are a lot of problems can be reduced back to the problem of computing the permanent. And so I give you a matrix, and the question, computational question, is just compute the permanent. Computing the determinant is very easy. Well, we know it can be done in quadratic time, but computing the permanent is known to be very hard. And so actually I skip a slide discussing that problem, but it's not so much related to the rest. Okay, so it's still your choice. You want to show proof? Yeah, so I want to prove this. Yeah, this the earliest and clearly the weakest theorem is that you take a non-symmetric case, right, plus minus 1 non-symmetric, and the probability that it is singular is going to 0. And it will, the proof will give something very small. Going to 0 slowly, but still going to 0. So so this is a short proof that I found a few years ago. The Combinatorial proof is more substantial. Yeah, so here's the idea. Okay, so I give this notation, the x1 up to xn are the rows, right? So if the matrix is singular, then actually, if I expose the row from x1 and then x2 and x3, then one of the rows should belong to the subspace spanned by the previous rows, right? So you have this upper bound, Pn less than the probability sum of all cases. Okay, everybody agree? Okay, now come a fact. If you, so this guy says the subspace of dimension d, then it contains at most 2 to the d plus minus 1 vector. Right, so for you to imagine, so here's you can view the plus minus 1 vector as the vertices of a hypercube, right? And you take any subspace of dimension d, and the claim is that it doesn't contain more than 2 to the d vertices from the cube. For instance, if you subspace of dimension 1, right, and it can contain at most 2 vertices, which is 2 to the 1. The proof is right here. Any vector in a d-dimensional subspace is determined by the set of d coordinates. Right? And then you have, for each coordinate, you have 2 choices, so that gives you 2 to the d. Okay, so why does it help? Okay, now we know that this guy have at most 2 to the I vectors in it. Right? So the probability will be bounded by 2 to the I over 2 to the n. Right? Because here you have 2 to the I, and you choose xi plus 1 from the whole cube, and you have 2 to the n choices. Right? So we have this. Now unfortunately this sum doesn't go to 0. Well, it is a geometrical sum, it's very easy to compute. So what is this sum, by the way? Well, it is a sum of half plus a quarter plus something, right? So it gives you 1 minus this. Well, it clearly, our aim is to have something that goes to 0, right? And it is something in the opposite direction. It goes to 1, and actually it goes to 1 fast. It's very bad. Right? It's very bad. Yeah, you're laughing at me, huh? Okay, but look. The sum is very close to 1, but it's dominated by the last few terms. It's a geometric series. Right? So if I can split the last, say, maybe log n term, and I can show separately that the contribution of the last k term is going to 0, then I am done, because the previous one doesn't contribute anything. Right? So now all I have to do is that now I take the last term, which is the largest one, and I'm going to bound it by 1 over square root 1 over log n to the 1/3 it will be enough because I have only log n term here to add up, right? So that part will give me something going to 0, and the rest I don't care, right? The rest comes from the geometric series. I don't really care. So yeah, so the whole thing now is just to prove this. But now what I will exploit is that this hyperplane or this subspace is a random subspace because x1 up to xn minus 1 are also random vector. Right? So I will have something much better than what I have here. Well, this fact is true for any subspace. But now I have to make use of the fact that this is a random subspace. Right? That is the core. Okay, so now I need a little definition which take maybe 2 minutes to digest, or 1 minute, I think 1 minute. I take an m by n matrix, or maybe I draw it on the board. So the matrix is like this, m and m, and I call it L universal. If I can do the following, I pick any L column, I1 up to IL, right? And for each column, I pick a sign, say either -1 or 1. I can write this sequence as I wish. Yeah, so there will be a lot of choices for the columns, and there will be a lot of choices for the signal I write in. And the definition say that the matrix is universal if no matter how I fix this thing, I will find a column, I will find a row x when the entry of x have sign exactly as this number. The entry after I1 will have negative sign, the entries of I2 will have negative sign, the entry of I3 will have positive sign. Right? So that is just a definition. We will see why it helps. Okay, so the fact here is that if I take L to be some parameter like log n, I take an n by n random, so let this guy be a random matrix that we care about. I will show that it is L universal with high probability. And the proof is one line, okay? If it fails to be universal, then actually I have to find an counter example, right? I can find L columns and a sequence of psi so that nothing match, right? So the number of choices for the column is n choose L. The number of size is psi sequence is 2 to the L, right? And the probability that nothing match. Okay, so if I look at the first column x1 or the first row x1, the probability that it doesn't match is this number, 1 minus 1 over 2L, right? Because if any of the position fail, then actually it will not match. Right? On the other hand, it have to fail for all n rows. Right? So I have that probability raised to the n. Right? And now you do the math, you take L to be a small number like log n, then actually this thing it will be very small, it will be less than 1 over n. Right? Yeah, because the last term dominate, you raise this to power n, which is something very important. So what does it say? It says that now if you just take the first n minus 1 row, right, then with this probability, any vector orthogonal to this row should have at least L non-zero coordinate. Why? If I take a vector, yeah, so let's say that I have a vector v which is orthogonal to x1 to xn minus 1, and I have only L minus 1 non-zero coordinate, say the first, non-zero, so this may be plus plus, maybe 2, 3, minus 5, something like that. But then I claim that this guy cannot be orthogonal to some of the axes because, well, I know that my trick is L universal, so I can pick this corresponding column from this row, from this coordinate, I can take the corresponding side, which is 1, 1 minus 1, 1. Right? Then I can find some column, some row, when I have matching entry here, and then the inner product of this guy with this is guaranteed to be positive, right? Because I multiply every entry with a number with the same sign. Okay, so we know that it should have at least L non-zero coordinate. Okay, and now I condition on this. I condition on this V will have at least L non-zero coordinate. Then what is the probability that the last row vector belong to the span of this guy? If xn belong to the span of this guy, it should be orthogonal to V, right? Because V is orthogonal to everything, right? And this probability, well, what is, let me write V as A1, the vector A1 up to AN, right? Then x times V is just the linear sum A1 C1 plus AN Cn. Maybe I write this nicer way, so maybe something like this. Well, maybe after the L coordinate is 0, and you just do this. And probability that this equal to 0 by the little root of first theorem that I wrote here, probability of the linear form to be 0 is over the 1 over square root L, not n, but L. But that already give you, well, L I fix to be log n, so that give you actually log 1 over square root log n, and here I aim for log n to the 1/3. You add all the constant and that give you some buffer zone. Yeah, but that is the proof. Okay, thank you very much.